Okay, thank you. So firstly, I would like to thank the organizers to invite me come to this nice program. This is my first time in Florence for this to visit this beautiful and historical city. And of course, I'm not a hydro person, but I would like to share you some recent work from my group, and which many done by my PhD student. And actually, the motivation is basically to check whether we can find some signatures of CEP when we use viscous hydro, to investigate the system in heavy ion conditions. Okay, I think I start from some theoretical studies of the critical endpoint. I think nowadays everybody believes that there is a kind of a critical endpoint at the finite baryon density. And I think the existence of the critical endpoint is that you need to have a first order phase transition at a high baryon density. So in that case, you need a kind of potential barrier for the at finite baryon chemical potential. So from this, I think everybody knows that this is a potential energy for nuclear system. So this value is due to the attractive interaction in the scanner channel, and this barrier, potential barrier, is due to the repulsive interaction from the electromagnetic field. And to our QCD system at the finite chemical potential, so there is, when you introduce this chemical potential, so this mu kind of plays the role of a kind of repulsive vector interaction. So this is a kind of experience from engineer model that when you introduce a repulsive vector interaction in the Lagrangian, then you will get an effective mu. So of course you can regard this mu as a repulsive vector interaction in the system. So when you increase mu, this means that the repulsive vector interaction increases, and then they will develop a potential barrier in your system. So that's there will be kind of forced vacuum decay to the true vacuum. Then you will have this first order phase transition. And of course, from lattice QCD, that we know that at no chemical potential, there is a crossover. And when you switch on chemical potential, you have first order phase transition. Then of course, you can expect that there is a critical endpoint at some point at the finite baryon chemical potential. So theoretically, we believe that there will be such kind of critical endpoint at the high baryon chemical potential. Okay, of course, this is there are some also experimental search of this critical endpoint. There are many programs. For example, the beam energy scan at RIC, and also the NICA program, and also FAIR, and also this HIAF is will be in China in Huizhou. So there are many programs to search for this critical endpoint, and also there are some lattice calculations to look for this critical point. And this is a recent work by this group. This is a lattice result. And this region kind of excluded through lattice calculations. And also, there are many non-perturbative QCD calculations that, including this PNG model, and also FRG, and also holographic QCD models. And we have some studies from effective models and also holographic QCD models. So all these non-productive framework that the strategy is like that. So firstly, at the zero chemical potential, you can fix the model parameters with lattice QCD equation of state. And then you extend to, and also this Baron number susceptibilities. So this is a kind of, if you expand the system as small mu over T, so this Baron number susceptibility will tell you the time expansion coefficients, basically. So when you fix the the parameters at zero chemical potential by equation of state and also by this Baron number fluctuations, so in principle you can predict this trend of this phase transition line. And then you can, by using such kind of framework, either by PNG model or FRG and also holographic QCD models, then you can predict the phase transitions at the finite chemical potentials. So this is a kind of theoretical framework. And okay. Lattice QCD at the moment, there is no critical point yet. I mean, because they cannot go to very big chemical potential. Yeah. Well, in principle, I mean, okay, at the zero chemical potential, that's for sure that it's crossover. But as I mentioned here, that if you have a chemical potential, this Baron chemical potential, it plays a kind of repulsive interaction, repulsive vector interaction. So basically, this repulsive vector interaction will develop a barrier in your potential energy, so that eventually you will have such kind of barrier, so that there will be a first order phase transition develops, right? So if you have such kind of a barrier in your thermodynamic potential, I mean, if you derive such kind of system equilibrium, so unavoidably you will have such a kind of first order phase transition. So if you have a crossover here at no chemical potential and you have first order phase transition at a high chemical potential, then you will have this critical point, right? So it's kind of very naturally, you will have this critical point at some point. Of course, okay. Yeah, this kind of theoretical predictions. Yeah, but they kind of believe that there is one. There is a critical point there at some chemical potential. Yeah, from this paper, but this is hidden here. This is just 2 months ago, I think. Yeah, in February. Yeah. I didn't know the technical, I didn't know the technical in lattice, yeah. Yeah, it's kind of nudge. Yeah, this mu over T is actually nudge, yeah. Is any lattice QCD people here? Maybe, maybe they can answer. Yeah, anyway, I'm not that person to this question. Anyway, so, okay, so this is a situation from experimental and also from lattice. And now we're back to the effective models. So from four-dimensional effective model and also five-dimensional holographic QCD models. So basically the strategy is that you fix parameters and at the zero chemical potential, and then you predict the critical endpoint. And it turns out that so if this, by using this strategy, then so it's kind of surprising is that any model you use, this location of the critical endpoint is actually quite close. So if we only focus on this 2+1 flavor case, so these points are kind of for 2+1 flavors. So these are from FRG and also from RPNG model and also from holographic QCD models from different groups. So I think these three basically, these 3 points are kind of based on Gabser's model. So basically introduce a kind of a Denton potential and to deform this metric. And we are using a kind of deformed metric to fix the equation of state of the QCD. And then, but eventually I think they are equivalent. So anyway, so it's kind of surprising that all these locations are kind of quite close to each other for the 2+1 flavor case. And of course, you can also predict to different flavor cases. And recently, we have another kind of more precisely to predict the location of the critical endpoint. And so this is HQ holographic QCD plus Bayesian calculation. And then this is kind of a precisely location of this critical endpoint. And this part is excluded region from lattice calculation. So this part. Even this is what you mentioned, the Einstein-Maxwell-Denton framework. Yeah, this kind of standard framework to introduce the chemical potential in holographic QCD models. Yeah, machine learning basically is kind of, I mean, to me, is a kind of to feed parameters. Yeah, it's kind of method. Yeah. So anyway, so it's kind of the location of the critical point kind of merges in this region that the critical chemical potential is around 700 MeV, and this critical temperature around 90 MeV. I mean, this is a kind of from all the non-perturbative QCD methods. So this is the situation. And this location is not excluded by lattice calculations, at least at the moment. Okay, so experimentally, of course, one of the main goals is to look for or to find where whether there is this critical point. So the signature, mostly they use this is net proton number fluctuations. So this is actually predicted by Stefan Misha Stefanov, and so this is the predict the signature that because this is a kind of standard picture of this critical endpoint. So this especially this safe this force how to say fluctuations over this second culminants. So this ratio there is a so this is a kind of very standard picture that. So on the left side, there will be kind of negative, and around this region, around this critical point, it's very there kind of a peak structure around this. So I will show you later a three-dimension plot, so you can see very clearly that anyway. So there is a kind of hollow kind of. Yeah, very negative, very deep negative region here, and a peak structure around this critical point here. So the typical structure is that this kurtosis will decreases with this collision energy because this is another increase of the chemical potential. And okay. Quantum matter. I will mention, I will go to there. I will go there. I will go to there. This is actually my main point of this talk. Yeah, okay. So then around, and then there will be peak structure around this critical point. This is a non-monotonic structure of this signature. If you use this net proton number fluctuations. So this is a signature. If you can find such kind of signature, then you will make a statement that the critical point will be there. Okay, no problem. Yeah, so this so because the signature, I mean the observers is actually cross this freeze out line. So basically, your observed protons will go through this freeze out line here in this region. So then you will get this kind of signature. Well, this is a kind of expectation. This kappa is C4 is basically this one. This thermodynamic potential derivative of force to this mu partial mu force. Yeah. Exactly. I will also go that point. Yeah. Maybe I will come to that at the end of, well, almost at the end of the my. Well, this liquid gas may be also related to low energy conditions. Yeah. So they have some negative proton number fluctuations. Yeah. Okay. Yeah, exactly. This is my main topic. I mean, yeah, I will go there. Yeah. So this is why we use hydro, right? But this part is still for equilibrium. I mean, from equilibrium, if you have this critical point, then you expect such kind of signature, right? Yeah. Okay. So of course you can use, so in our work, we use this equation of state from this Pinger model. You can also use equation of state from any other models with a critical point. So anyway, so that's just a model. And if you have such kind of, so this is a typical structure for this net proton fluctuations. So here, this part, this is very negative, this deep is a very hollow. So this is very negative in this part. So basically, if you have a critical point here, so on the left hand side, this part is very negative. And on the, how do you say, around this critical point, it will develop a kind of peak structure. So you would expect such kind of non-monotonic structure if your observables kind of along the freeze out line. So this observable is actually very sensitive to the freeze out line. So the relation between your freeze out line and the phase transition line is very sensitive. I mean, so if you choose a different freeze out lines, then you will get a different structure of your observables. So that's kind of from thermal equilibrium system. Okay, now, so we go to hydro because as you mentioned that, so the real heavy ion conditions, the system is kind of evolve with time, and it's not, it does not stay in equilibrium. So the motivation of our work is basically we combine our equation of state with hydro. So this is basically, I think Chun showed yesterday the main foundations of this hydro. And so we are kind of doing kind of exercise that, so we use a kind of hybrid model. So we have some initial conditions from this smash, and then we use hydro to evolve the system, and then the observables are kind of from this sample. After this sample, then have this proton observables. And this is hydro code that we used actually. This is called C-air viscous. So this is developed by CCNU, this Pang Nonggang. And he developed this C-air viscous, and we just use this model. And we input, so we input the equation of state from some effective model. I mean, this model, this is from our Pinger model, any other model you can use. But in any case, this equation of state, indeed, there is a critical point. So basically, this equation of state carries the information of the critical point. So we combine this equation of state and we insert this equation of state into this hydrodynamics. You mean the right-hand side? Mm-hmm.
So how do you handle the fluid elements that go on the right?
Yeah, because yeah, maybe we cannot go there because freeze out line is always below the phase transition line. So basically, so let me see. Because okay, here. So because the freeze transition line, so this is a freeze transition line, but the freeze out, because freeze out is kind of for protons and hadrons, right? So this freeze out line is always below this freeze transition line. So you cannot go to where your observables will not go to the right-hand side of the critical point. Hmm? Simulation, well, we, okay. Okay, in principle, yeah, you can go there. But in practice, so we only check the observables along this line. Yeah. Okay. Uh-huh. You mean mix the phase at the finite chemical potential? Yeah, sure, sure, sure. If you have a first order phase transition, in principle, you can have such kind of mixed phase, hybrid phase. Yes. Yeah, you can have mixed phase. Yes. Yeah, because I didn't get to the main point yet. Okay. So then you run the hydro. I mean, you have the initial condition from Smash. So this is open source. You can get from the open website, and you can use this as our initial condition. And then you insert the equation of state. Actually, we use two different equation of state to compare the results. So one is, I think, mentioned yesterday by Chen. This is a numerical equation of state from Lattice QCD. And but this equation of state, there is no critical point. And we also use this equation of state which has a critical point. So we use these two equation of state to compare the results. Okay, then so these are parameters we use for the simulation for the hydro part. So and this spectral turns out for different condition energies not very bad. I mean, it looks good. And then with this, then we can observe this net proton fluctuations. Train, you can say that indeed there is no this peak structure. So, okay, so from equilibrium, you can expect that you will have such kind of non-monotonic structure. But if you use this hydro, then whether you have this critical point in your equation of state or without. So this brown is for the equation of state with without critical point, and this blue one is with this equation of state with critical point. But you see that all, I mean, for both cases, this fluctuations, this net proton number fluctuations, monotonically decreases when this condition energy decreases. Yeah. So yeah, but anyway, so and also this line is from the music by another group, and you say that whether you use different hydro or whether you use different equation of state, whether you have a critical point or without critical point, so this so you don't have such kind of non-monotonic behavior of this net proton baryon number fluctuations. Okay. And then, of course, last year, 1 month later, there was a CEP conference, and this is latest data from STAR collaboration. And indeed, such kind of non-monotonic behavior kind of disappear. Of course, there is a kind of kink here. So I will also come to this kink later. But anyway, from this latest data above 7.7 GeV data, so there is no such kind of non-monotonic behavior. No, at least there is no such kind of peak structure. Okay, so this is, yeah, Rick from STAR. Sorry? Oh yeah, this is Rick data some years ago, maybe 5 years ago. There is a kind of such a peak structure here. Kind of indication of this peak structure here. Yeah. Okay, anyway, so because the motivation of our work is actually to see the peak structure, but eventually we didn't see the peak structure. It's kind of bad news for us. So we spend kind of more than half a year to check these results. But anyway, so we didn't find anything we can improve. So then we put it into archive. So, but the good news is that this STAR data so appeared 1 month later, kind of in agreement. So our results are kind of in agreement with the data, except this kink structure. So the equation of state, in the equation of state, this blue one, we have this critical point. But it turns out that, so this equation of state without, yeah. Yeah. So kind of equation of state independent, yeah. Okay, of course, we need to understand why such kind of peak structure, which you expect to appear if you have a critical point, but why it does not show up in your experimental data. So then, so we carefully to analyze the reason. So why we didn't see the peak structure. So eventually we found that our freeze out 9, our freeze out is actually very far away from the location of the created endpoint. So that might be the reason that we cannot see the peak structure. And also this is a kind of isentropic line, or the evolution of the system when for different condition energy. So this far away, anyway, it's far away from your from the critical point. So this might be the reason that we cannot see the peak structure. And another possible reason is that maybe because this critical point is predicted by chiral phase transition. So, but when we come to the real system, this because the system will go through the coagulant plasma to hydronic phase. So there is a kind of quark matter to hydronic matter. So maybe if you have a signature, but this signature will be washed out by hydronization. So this is might be another reason. So, but anyway, so we didn't see this peak structure. But of course, we are also still waiting for experimental data around the 5 GeV for this condition energy. So maybe for the NICA or in the future from HEF in China. So anyway, so at least at the moment, there is no data around the 5 GeV. But from equilibrium, so the peak structure shows up around the 5 GeV. So, okay, anyway, so maybe in the future, so if you see a kind of a peak structure around the 5 GeV, that might be a signature for the critical point. This is a prediction from the model, from effective QCD models. Engineer and holographic QCD, and also this FRG calculations. But the location of the CEP almost the same, yeah. This result is from FRG from this is from the freeze out 9 you choose. Freeze out 9. Because as I showed here, so this peak structure is very sensitive to the relation between the freeze out 9 and your phase transition 9. So yeah, so the anyway, the renormalization group or functional renormalization group or FRG or DSE or HQCD or other effective QCD models, just to predict the location of the critical point. So if you have the location of the critical point, you will have such kind of structure here. And the observables actually determined by the freeze out 9. So, I mean, so how the observables go through this, how to say, these mountains, basically. Yeah.
This is why I understand why they explain by thermodynamic calculation across the phase of time. Like if you produce electricity or whatever you produce in a box at that temperature, right? And then we were able to vary that temperature with the collision energy, I would agree, but what we do is this complicated dynamical system which just passes through the critical point.
Mm-hmm.
So this is why this for your calculation I can understand the high simulation of simple thermodynamic calculations plotted across physical line. understand why they are good predictions for what is mentioned.
Well, oh, okay, this, I don't know. I don't know the answer. Yeah.
I think there's this kind of this hydroblast, so all this with some fine hydrodynamics. In the hydroblast kinetic. That's very hard to do.
Yes. Okay. Yeah, that's good. So many people are interested in this topic. That's very nice. But anyway, yeah. 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 Exactly. Exactly. Yeah, yeah, yeah. Yeah, this can be improved in the future. Yeah, exactly. Yeah. Okay, this is for the to understand the result. And also this quark matter talk, I think somebody went to quark matter last week. And you may notice that there are also some data at no energy condition energy around 3.9. And actually, this data is actually already, well, some data already published in several years ago. So anyway, so the interesting part is that there is a kind of a negative kurtosis. So this ratio is negative. So this negative actually is very interesting. Maybe come to Jean Paul's question about this liquid gas. Actually, 2 years ago, we investigated these two critical points. So one is for the, this critical point is from quark matter to hadronic matter. And there is another critical point which is described by Vanashka model. This is the nuclear matter, this liquid gas phase transition for the, how do you say, for nuclear matter. And there is another, the second critical point here. And if you use this result 9, and then you will find that there is kind of a negative kurtosis, maybe related to this data. This is what we proposed several years ago. And this negative kurtosis might be a kind of probe of the first order phase transition for nuclear matter liquid gas phase transition. This is what we proposed. Okay, and now we we combine this Vanashka model to hydro. Of course, at the moment, it's very difficult to use hydro at a very low condition energy because below 4 or 5 GeV, it's kind of you cannot run the hydro successfully. So basically, we can only run hydro at around above 5 GeV condition energy, and so my student he has another result, recent result. So he uses this equation of state from Valashka model. So basically, this is for hadronic degrees of freedom. And then he found a kink structure here. So this position is not exactly at this 19.6 GeV, but this is around this 14 something GeV. So, but anyway, this is kind of a hint that so this kink structure might not due to critical point, but might due to the degrees of freedom changing that below. So you see the kink structure that above this kink, so this is decreasing, but below this kink, this trend is increasing, right? So this kink structure might indicate that below this kink, so this system is described by hadronic degrees of freedom, and above this kink, this is the system is described by quark degrees of freedom. So this is a kind of hint. But because there are still many technical problems, so we are still checking, carefully study this behavior, and hopefully in the future it can be confirmed in the future. Okay, so as I said that maybe, so you have this critical point. This is a kind of a prediction from equilibrium, and also this is a prediction from your chiral phase transition. But this signature, so basically from theory, your critical point might be there, but you will not see that from experiment. If you use this kurtosis or this net proton number fluctuations, because these observables, the system will experience this hydronization. So you need to take into account the confinement, deconfinement phase transition. Of course, this part, nobody understands very well on this phase transition, deconfinement, confinement phase transition. So anyway, I think if you use net proton fluctuations as a signature, you may never find your critical point. So this is kind of my understanding. So of course we need to find some other signatures that free of hydronization. So this jet quenching might be, or jet quenching, or some kind of photon, or some lepton observers might be possible candidates that because this pass through the medium and will tell you some information about the medium. So if the system really experiences critical point, so there will be some kind of signatures from these observables. So these are calculations from holographic QCD in this paper with my previous students that. So we use this holographic QCD model with a critical point for different flavors. And we see that there is a peak structure at this critical, yeah, okay, it's almost the end. Yeah, okay. Okay, okay. So there are already some from that JET collaboration that they investigated this jet quenching parameter for 10 GeV condition energy, and they observed such kind of structure. But if you for example, if you can have data at condition energy around 5 GeV, so maybe you can get such kind of a peak structure for jet quenching. So then maybe then you can conclude that you have such kind of critical point. So this is, of course, you need to combine theoretical calculations and also experimental data. So I think this is one of the examples that you need to find some other signatures that free of hydrogenization. Because if you, the system experience hydrogenization, so you may not observe that. Okay, the summary, so from theory predictions that the critical point should be there. I mean, I'm a theory, so I believe that it's there. And kind of all the non-perturbative QCD models predict the prediction for the location of the critical point are almost converge at some point. So critical point is there, but the thing is that how can you find it from experimental data? So at least from the data from RIC at the moment, there is no such kind of signature for critical point. At least no explicit signature above 7.7 GeV. And of course, at no condition energy, for example, 3.3 GeV or 3.9 GeV, some kind of negative kurtosis, so that might be a signature for liquid gas phase transition or not. I don't know, but anyway, so it's still a puzzle. So why the kurtosis is negative at no condition energy? I think at the moment, nobody really understands that. Of course, your community gives negative, but I don't know why. So why there is such kind of negative kurtosis? Okay, and another point is that the kink of the net proton number fluctuations might be a hint that this is a position that the quark degrees of freedom and hadronic degrees of freedom separates at that point. So of course, we are still running the code, and we hope to answer this question in the future. And I think this is what I want to emphasize, that so I think we do not need to focus on this net proton fluctuations or the signature for CEP. So we need to find other signatures for critical point. Okay, with this, I thank you for your attention. Okay, so that's all. Okay, thank you. Mm-hmm. Mm-hmm.
You may really stay in the hydronic point without crossing, so without using any system which is of local dynamic equilibrium in the plasma phase.
Mm-hmm.
So my question is, when you go to your lowest end,
Mm-hmm.
so how deep you went to plasma?
Okay. Yeah, so one thing I didn't mention that is that for liquid gas, I mean, if you have this liquid gas phase transition and you have a critical point here, so the signature of a critical point for kurtosis is always the same as this one. So this is a universal structure for the critical point moment. So where it is? Yeah, here. So you can regard this is a liquid gas critical point. And so if your phase out line goes through this part, you will have, I mean, in this region, you will have negative. Mm. Oh, it's here. Okay, moment, I will come there to there. So here I want to mention that for liquid gas phase transition, first order. So because the system is already in hydronic phase, so you don't need to consider, the phase transition from quark matter to hydronic matter. So this signature can remain in hydronic matter. I mean, for this liquid gas. So it's kind of maybe crazy because I actually reported this kind of idea. Yeah, I mean, you only have hydronic matter, nuclear matter, basically. Oh yes. Okay, that one I go there. Yeah. Oh, sorry. So we have this isentropic line for the evolution of the system. So here you see for point. So this is for 7.7 GeV. So yeah, you have okay. So yeah, but your observables is here. So basically, yeah. 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 But the initial temperature is high, still for 7.7. Yeah. Mm-hmm. Mm-hmm. Exactly. Yeah. But unfortunately, the hydro cannot go to no energy. Yeah, it doesn't work. Mm-hmm. Exactly. Yeah, we looked at here. So we looked at here. I mean, 2 years ago, with one of my previous PhD student. So this one. So this is for we have a kind of hybrid model with Pinger model and Walashka model. Yeah. Yeah, this is the data. These are data for this barrel number fluctuations. Yeah, we can put the latest data here, but anyway. So these are data. we can put the data here. We can put the data here. Yeah.
No, I think it's talking about the
Okay. Yeah, yeah, yeah. Exactly. Yeah, yeah, yeah. Yeah. Yeah, yeah, yeah. So exactly. I totally agree with you. Yes, yes. Exactly. Mm. Yeah, yeah, yeah.
the big debate, but it's for the phase transition, and it's complicated as you approach the critical point, because binding forces weakens and the system becomes fragile. There are actually but it helps exploding the system. So there's been a lot of calculation, statistical analysis, liquid gas on the lattice gas. There have been a lot of studies. Hydros at least all of them.
Mm-hmm.
For the down to the base, yes, it's well understood because
Mm-hmm. Yeah. So this data are for 3 point some GV. Yeah, but this is a negative. So this is not understood. I mean, so we think that this might related to this liquid gas. But do you think this is crazy or not? I mean, whether this negative kurtosis, this is data. But because, yeah, so, yeah, that deserved to do good. Mhm. So you mean the scaling, whether the scaling will break or not? 5GV maybe works. I mean, this NC scaling, this N scaling maybe works, but below this scaling does not work. Yeah.
usually people just think about the point effect pressure, thermodynamic violence, but maybe transport is more. Lorenzo mentioned, no viscosity evaluation. The critical function that affects all the transport coefficients. This is maybe kind of understood. Also a good check to see change transport can be measured.
Yeah. Yeah. This maybe can improve this result. Yeah. ISO. You mean isentropic? Okay. Oh, sorry. Wrong direction. This one? Sorry? It's somewhere, let me see. It's, yeah, I think it's here, this one, somewhere here. Yeah, if yeah, maybe for no energy, for example, 5 or something GeV. So maybe it will go through like this. I mean, if you have this system evolves like this, cross this critical point, then you may find the signature. Well, this is checked from the code. From the code, I mean, from the hydro code. So you can check the temperature, you can have the temperature, and then the chemical potential for the system evolve with time. Yeah, so this is, yeah, average temperature. I don't know. Yeah, I can ask my student to check, but I cannot run the code. Hmm?
Sampling, you're converting, we're going from hydrodynamics to sampling. This data should have it's your question.
I didn't quite get this question, so. So what is the delta? What is the delta? So what do you mean delta? I didn't get the point. Yeah, exactly. Yeah, exactly. Okay. You mean delta F? Well, I think at the moment we don't. Yeah, maybe trend can help. I think at the moment we don't have such. Yeah, exactly. So we don't have this delta F. Yeah. Okay, anyways, thank you for your question. Okay, thank you very much.